In this video, we're going to talk about an area of health psychology called psychoneuroimmunology, also called PNI. PNI looks for connections between psychological factors in the functioning of the nervous system and the functioning of the immune system. PNI encompasses many areas, including psychology, neuroscience, immunology, physiology, pharmacology, psychiatry, and behavioral medicine. In this video, we'll continue our discussion of what stress can do to the immune system. First, I want to give you a little information on the immune system and how it works. Then I'll give you the background on the field of psychoneuroimmunology, and then we'll talk about some of the modern work in PNI, looking at the effects of stress on immune functioning. The primary job of the immune system is to defend the body against infectious agents like viruses, bacteria, and parasites. The first step in doing that is figuring out if something it encounters is a normal part of the body or an infectious invader. If it's an invader, the immune system must attack it. Sometimes the immune system screws up and attacks a normal part of the body. That's what happens in an autoimmune disease. Parts of the body that you need are attacked by your own immune system. Celiac disease is an example of an autoimmune disease. When individuals with celiac eat gluten, their immune system attacks the lining of their small intestines. There are two types of immunity, innate and specific. Innate immunity is your inborn resistance to pathogens. You're born with innate immunity. This kind of immunity is your first line of defense against pathogens. It responds in the same way for all types of pathogens, which means it acts in a non-specific way. However, some pathogens might get past this first line of defense. There are different kinds of innate immune defenses. The largest one is your skin, which prevents pathogens from entering your body in the first place. Another innate immune defense is inflammation, which is a local reaction to infection. When inflammation happens, white blood cells enter the tissues and attack the infection. A clot forms around the infection to keep it from spreading to other parts of your body. Inflammation is what happens when you cut yourself. After you cut yourself, your skin reddens, it swells, it'll become filled with pus and clots. Because innate immunity is a non-specific response, it can act very fast as a first line of defense. However, many pathogens can get past it. The innate immune system mainly has four types of cells: natural killer cells, macrophages, antigen-presenting cells, and the FILs, which are cells that act as suicide bombers. Let's start with the natural killer cells. These cells are like soldiers. They patrol around looking for cells that don't look like them, cells that are invaders rather than normal parts of the body. So natural killer cells look around to see whether a cell is, to use an analogy from the Cold War, American or Russian. If it's Russian, then they go up to it and basically destroy it from the inside out. Natural killer cells are part of the innate immunity because their response is the same for all kinds of invaders. These cells don't do different things for different kinds of invaders. Macrophages are basically like little Pac-Men. Macrophages kill invaders by eating them and digesting them into harmless little bits and pieces. Antigen-presenting cells are like little tattletales. They include a bunch of different kinds of cells that do the same thing. These cells figure out who the invader is, and they report back to Mission Control about who the invader is. However, they don't just tell Mission Control who the invader is, they also take a piece of the invader to show Mission Control. That little piece of the enemy is called an antigen, so the name makes sense. They're antigen-presenting cells. They present the antigens to other cells. The suicide bombers are called eosinophils, basophils, and neutrophils. But basically, these phils go up to a cell and release destructive enzymes that tell a cell to degranulate, or just fly apart, basically. They're suicide bombers because the enzymes are so powerful that once they release them, everything near these enzymes degranulates or dies, including the phils themselves. When you have a cold and you have tons of snot, that's all these little suicide bombers. So basically, your innate immunity is a battle zone. All these cells are communicating with each other, leading to many chemicals flowing around. These cells are self-destructing, killing and eating invaders, which is why the skin around your cuts gets inflamed. So that's a quick, simple overview of the innate immune system. It's fast, it's the same every time, but it's imperfect. When invaders get past innate immunity defenses, they have to contend with another form of immunity, adaptive immunity. You're not born with adaptive immunity, but you have to acquire it based on what specific sorts of pathogens try to invade you. Adaptive immunity is a slower process than innate immunity. So, how does your adaptive immunity work? Well, first, the tattletale cells, or the antigen-presenting cells, travel around the bloodstream and go into the lymph nodes, which are all over your body. The antigen-presenting cells roll around, bumping into the cells that are hanging out in your lymph nodes, some of which are a kind of white blood cell called a helper T cell. The tattletale cell runs around your lymph nodes, showing different helper T cells the bit of the invader that they collected until they find the right kind of helper T cell that knows how to kill this kind of enemy. Different enemies require different tactics. The right helper T cell will have receptors solely for that kind of infectious agent. There are 1,015 different kinds of helper T cells in humans, but among all those kinds, there are only a small number of each kind that can deal with specific invaders. So the goal of the tattletale cell is to find the right type of helper T cell to tattle to, the kind for just that type of invader. After the correct helper T cell is identified, it then builds an army. First, they make a whole bunch of copies of themselves, so they create clones of themselves. And then together, they make just the right kinds of killer cells for the invader. Some of those cells are a kind of T cell called cytotoxic killer cells. Cytotoxic killer cells can be used to attack and then destroy the invader. Those kill the invader like Jack the Ripper, basically. They directly kill it, and sometimes they even kill them by eating them. Another kind of cell that's part of adaptive immunity is a B cell, which kills by poisoning invaders. B cells are activated by helper T cells. They poison the invader using a special poison made specifically for that invader. That special poison they use is called an antibody. Well, the problem with this process, with the adaptive immunity process, is that it takes a lot of time and energy to build an army. While clones are being made, the enemy may multiply. However, to speed things up during future attacks by the same invaders, the adaptive immune system creates memory cells. Memory cells are created from B cells and T cells for a particular invader. So if your body ever encounters the same invader again, it can fight it off very quickly. The immune system doesn't have to go through the long, slow process of finding the right T cell and then building an army. These memory cells are what we take advantage of when we get a vaccine. we get a mild version of some infectious agent, which makes your immune system prepare for future attacks of that agent. So if the agent ever comes back, your body is ready right away to fight it off, because it's already made B and T cells and the resulting memory cells for that invader. Okay, so that's how the immune response works. In the rest of the video, I'll show you different ways that your thoughts or stress appraisals can have an effect on your immune system. The first way is through some sort of learned association. There's a classic study that really started the field of psychoneuroimmunology. It's really cool, but it's a little complicated, so I want you to stay with me here and don't panic as I go through this. First, think back to Pavlov and his work on classical conditioning. You remember that from intro psych, probably? Let's take a moment just to review how Pavlov's dogs demonstrate classical conditioning. Before doing any conditioning on the dogs, Pavlov would ring a bell, the dog would hear a bell, and this was just a neutral stimulus. The dog wouldn't react to this bell before conditioning. Similarly, when the dog saw food, which before conditioning is an unconditioned stimulus, they would salivate. During conditioning, Pavlov would ring a bell and present food at the same time on multiple occasions. So the dog would hear a bell, it would see food, and it would salivate during this conditioning process. After the conditioning, Pavlov would ring the bell, now a conditioned stimulus, without showing any food, and the dog would salivate just to the sound of the bell alone. Basically, they were conditioned to salivate to the sound of a bell. So the animal's thoughts affected a physical response. Nobody talked about Pavlov's work in terms of health conditioning or health psychology then, and nobody really does now either. But it's a good example of an early version of a study showing how mental experience can affect physical symptoms. Okay, now on to the study I alluded to. The person who did this work was Robert Ader. And, like many other remarkable discoveries, Ader discovered what I'm about to show you completely inadvertently while he was studying something else. Ader was looking at taste aversion in rats. In taste aversion, you learn to avoid foods that make you sick. This can happen in just one trial, as opposed to in classical conditioning, you have to be conditioned by being presented with multiple trials of the bell and the food at the same time. So this is a particularly unusual form of conditioning because there tends to be several hours between when you eat the food and when you get sick from the food that you eat. But still, you don't want to eat that food again anytime soon. Taste aversions can happen even if the food didn't actually cause the sickness, but instead you just happened to eat it at some point prior to getting sick. So if you happen to catch a stomach bug, the food you were eating not long before your symptoms appeared may seem unappetizing to you for a long time. Anyway, back to this story. Robert Ader was studying taste aversion in rats. Before conditioning, he gave them sugar water, and it had no effect on them. Next, but also before conditioning, if he injected them with a nasty drug, this created nausea in the rats. During conditioning, he gave them sugar water and then injected them with a nasty drug that would make them sick. After conditioning, he gave them sugar water alone, and lo and behold, the sugar water alone would make the rats sick. So he was giving rats something tasty, sugar water, and then later injecting them with a drug that made them sick. And then just by drinking the sugar water alone after this conditioning of taste aversion, the rats would get sick just by drinking the sugar water alone. Originally, Ader was only interested in measuring how long this nausea response would go on. So he was interested in creating this taste aversion just on one occasion, and then seeing how long these rats would display this taste aversion after the initial conditioning. So to study this, he had two groups of rats, a conditioned group and a control group. On the first day of the study, the conditioned group of rats was given sugar water alone, and then an injection of the drug that made them sick. The control group of rats was given sugar water and then an injection of saline solution, which should have no effect on them whatsoever. So he had some rats that he conditioned to get nauseous whenever they had sugar water, and some rats who weren't so conditioned. Then, every day, for 50 more days, Ader gave them sugar water. He wanted to see how many days the conditioned rats would continue getting nauseous just from sugar water. Now remember, the conditioned rats only had the drug one time, on the first day of the study, and the amount of this drug that he gave the rats on that day was very small. The rats were sick that day, but they recovered rapidly. So what happened to the conditioned rats during those 50 days? Well, the rats who had only been conditioned on that one occasion, only had that one injection of the drug, suddenly started dropping dead on him. This was a completely bizarre response. There's no reason rats should be dropping dead from a daily drink of sugar water. So what was going on? Well, at this point, Ader realized that the drug he was using was an immunosuppressive drug. An immunosuppressive drug lowers your immune response. That is, it keeps it from fully fighting off potential threats. However, there's no reason a rat should die from one tiny injection of a drug that has immunosuppressive abilities. So Ader thought that maybe what he had done was condition the rats to have an immunosuppressive response every time they drank sugar water, and maybe that's why they died. So here's what he thought might be happening. Before conditioning, the sugar water doesn't do anything, but the shot of the nasty drug suppresses their immune system slightly. Then during conditioning, the sugar water and the drug together led to suppression of the immune system. After conditioning, the sugar water alone led to immune suppression. Well, to say that you can condition taste aversion is one thing, but to say that you can condition immune response is quite another. A conditioned immune response would mean that there are links between the mind and the body. Before this, the immune system was thought to be entirely separate from the mind. Although compelling, Ader's study wasn't conclusive. So what was inconclusive about the study? Well, the two groups differed in terms of nausea. Maybe the rats who died were dying of nausea. This seems unlikely, but it needs to be ruled out with another experiment. So Ader never measured the rat's actual immune response, so he couldn't be sure that's why the animals died. Furthermore, these rats could have died due to some bizarre delayed effect of the drug that caused the rats to die. So Ader and Cohen conducted some more studies controlling for the things I just mentioned. In one, they controlled for the nausea difference between the two groups by doing a study with a different drug that leads to nausea but doesn't suppress the immune system in the control condition. Of course, those rats were fine, other than constantly being nauseous. So these rats were getting nauseated, but not dying and not showing any decreased immune response. They also conducted a study to control for this bizarre delayed reaction that the drug potentially had. In this study, they also made sure to measure the rat's immune response. So they had 3 groups of rats. On the first day, the conditioned group got sugar water in the drug, so they should be conditioned to have a response in reaction to sugar water that they receive on all of the following days. The non-conditioned group got plain water and the drug. So on the first day, they got plain water paired with the drug injection. Then on following days, they got sugar water, which wasn't paired with anything for them. So they should not be conditioned to have any particular response to the sugar water. However, if there are long-term effects of one shot of the drug, this group should also show those effects too. This group should also die out in the long run if this delayed reaction hypothesis is true. The placebo group had plain water and then an injection of saline. This group controls for anything about getting injections that might be causing this effect in rats. So with all these careful controls, he showed that, in fact, you can behaviorally condition an immune response. Rats in the conditioned group showed a suppressed immune system, and this breakthrough led to the field of psychoneuroimmunology. This field looks at all the ways in which psychology has a direct impact on the immune system, which underlies your body's ability to fight off disease. In the last video, we began talking about the effects of stress on immune function. I talked about studies showing that chronic stress increases people's likelihood of getting a cold if they are exposed to a cold. So, chronic stress can suppress the immune response. But it's important to realize that in this cold study, the researchers didn't measure immune response. In this study, they measured whether people got colds, and from that they inferred that people's immune response must have been suppressed, or else why else would they have been getting these colds? It's not a bad inference to make, but it's still an inference. P&I studies have been done in which they actually measure the immune response itself, in addition to some illness outcome that results from the immune response, or suppression of the immune system. This is a very complex area to do research in. You have to be extremely careful when you take your measurements in each of your subjects, and you have to carefully choose a reasonable selection of immune measures to use. You never want to use just one, but you don't want to pick so many that your study turns into a giant grab bag where anything can happen. Now I'm going to tell you about a few different studies that measured immune functioning. The first two studies look at the effects of chronic stress on wound healing. Specifically, they measured a particular immune substance called a pro-inflammatory cytokine, and more specifically, interleukin-1. Cytokines are interesting substances, but what I'm going to tell you today about them is very oversimplified. The real story is way too complex to get into here, and we're more interested in how stress or psychological factors affects your health. A pro-inflammatory cytokine is a substance produced by the immune system that plays a role in both adaptive and innate immunity. In the adaptive immune response, they help communicate with other immune cells and basically tell them how to respond. In the innate immune response, they cause inflammation, which is why they're called pro-inflammatory cytokines. Inflammation might seem like a bad thing to you. When things are inflamed, they're red and hot and you're sore. You might get a fever or feel tired. You might have trouble doing things and you just don't feel like eating or drinking. However, inflammation is actually a good thing. It's adaptive because it aids in healing and fighting off infections. For example, a fever occurs because infectious agents tend to grow more slowly under those high temperatures. The symptoms of inflammation that I just described are exactly the ones that you feel when your body's fighting off an infection. But those symptoms aren't the infection themselves. They're your body's strong immune response to the infection. So these are the basics of pro-inflammatory cytokines. In one study, researchers compared wound healing between two groups. One group contained 13 women who were stressed because they were caregivers for a family member with Alzheimer's. The other group contained 13 women who weren't severely stressed. The groups were matched on age, income, and other factors. The researchers gave subjects a small, standardized wound at the beginning of the study, and then they simply measured how long it took for that wound to heal. They made the wound using something called a biopsy punch, which is routinely used in dermatological work. This punch sort of pinches and then cuts you a bit, but importantly, it makes the exact same size wound every time. They found that stressed people, so the caregivers, took an average of 24% longer to completely heal the wound, which translated into 9 days longer on average. And this graph shows the percentage of subjects who had fully healed. And you can see that each week, which is the x-axis, a greater percentage of controls were fully healed than the caregivers. The y-axis is showing you the percentage of subjects with fully healed wounds. But wound healing is really just the illness outcome, not the immune function itself. These researchers also measured the amount of interleukin-1, a pro-inflammatory cytokine that was produced by the blood around the wound. In this study, the caregiver's blood produced less interleukin-1 than the control's blood. Remember, we want to produce more interleukin-1 because that means our body's creating an inflammatory response, which helps us heal faster. So based on these results, it appears that stress actually alters an important immune response, the production of interleukin-1. However, you guys might be thinking this yourselves already, there's a flaw with this study. Specifically, there was no random assignment. Thus, there could have been other pre-existing differences between the two groups. For example, maybe the caregivers were getting less sleep, maybe they weren't eating as well, maybe they were smoking more often, and it could be that those things caused the differences in wound healing. In a different study, researchers compared dental students' wound healing during exams to their own wound healing during summer vacation. In this study, dental students' wounds were compared during summertime and exam time. There was about 6 weeks between the two wounds, so every subject was his or her own control. Each student got a small wound during summer break, and then about 6 weeks later they were wounded again 3 days before an exam. The researchers then measured the amount of interleukin-1 in the blood around the wound during both the summer and exam times. The researchers found that wounds placed during the exams healed 40% slower than wounds placed during the summer. Not a single student healed as faster during exams than during the summer, which is a very powerful result. In addition, during exams, the students produced less interleukin-1, this important wound repairing substance, than they produced during summer. Specifically, their interleukin-1 levels decreased an average of 68% during exam time. This result is particularly remarkable because exams aren't really thought to be a very major stressor. After all, these were students who had a whole history of taking exams and doing well on them. To put it another way, if you've made it to dental school, you can't be a complete flake when it comes to your schoolwork. Also, the stress wasn't terribly long-term, especially compared to the stress of caring for a sick relative. It's remarkable that this kind of mild stressor can have such a powerful effect on wound repair. In this study, we know that it's not differences in the people that are causing the differences in wound repair, because it was always the same people involved. Everybody was compared to him or herself. However, there could still be other differences. Again, the people might be more sleep deprived during exams than during the summer, or maybe they weren't eating as well. Also, maybe there are seasonal differences in how well your body repairs wounds. Maybe it just works better in the summer when the weather's better. But this is pretty unlikely, since the exams occurred only 6 weeks after summer vacation. Notice that each of these two studies have their flaws, but each one has a different kind of flaw. One had seasonal changes as a problem, but the other didn't. One had two groups of people that might not have been equivalent, but the other didn't. Since both studies point in the same direction, we can feel more confident about their results. This is called convergent evidence, and it's a crucial test of any finding. But you might be thinking, those are just little superficial wounds. Does stress influence the healing process of bigger wounds, like surgical incisions? Well, there is evidence that it does. A study by Broadbent and colleagues measured participants' level of stress right before undergoing a surgical procedure to repair a hernia. After the surgery, they measured the participants' wound fluid, perceived stress, pain, and recovery speed. They found that the more stress patients reported before the procedure, the longer it took the incision to heal, and the more pain the patients felt. Also, these more stressed patients had less interleukin-1 in their wound fluid. Because interleukin-1 is a pro-inflammatory cytokine, having less interleukin-1 means that these patients had less inflammation, which slowed the healing process. These studies suggest that stress affects the immune system by suppressing it. And that's fine as a general take-home message about the effects on stress on immunity. However, the story is more complicated than that. To illustrate this, I want to provide you with a study that looks at the effects of acute stress on immune functioning. Remember, acute stress is the quick on, quick off type of stressor. The acute stressor looked at in this study was people's first time skydiving. This is something that most people would find unbelievably stressful, but the stress only lasts for a short, constrained amount of time. Participants were 45 people who were planning to try a parachute jump for the first time. Researchers monitored their physiological responses before, during, and after the jump. To measure immune functioning, blood samples were taken 2 hours before, immediately after, and 1 hour after the jump. In addition, they had electrodes placed on their chest with a portable recording system so that their heart rate could be recorded continuously. Finally, they had a catheter inserted into a vein so that blood could be sampled continuously with a portable pump to measure levels of the hormones of the sympathetic nervous system, epinephrine and norepinephrine. Remember, those are the hormones that increase in response to stress. They help to mobilize energy. These hormone and heart rate measures were taken from 2 hours before the jump to 1 hour after. So, what did they find? First, let's look at heart rate. Just keep in mind that the average resting heart rate is between 60 to 100 beats per minute. Under stress, we would expect heart rate to go way up. Increased heart rate would be a typical stress response. Here's what happened to heart rate throughout the time leading up to the jump and then right after. Each tick mark on the x-axis is 10 minutes, and the vertical dotted line shows the moment when the person jumped out of the plane. The y-axis shows participants' heart rate at beats per minute. You want to focus on the line with the black squares. The line above it's simply the standard deviation, which you don't need to worry about. In the graph, you can see their heart rate is slowly increasing as the time to jump out of the plane comes closer, and then it skyrockets as they exit the plane, as high as 152 beats per minute during the jump. This is a very strong response. And you can see that in the hour after the jump, it makes its way slowly down to baseline again. So this is exactly what we would expect to see in response to stress. Now let's look at the hormones of the sympathetic nervous system. I'll show you two of them, epinephrine, again, you may know this as adrenaline, and norepinephrine, which you may know as noradrenaline. Since these two hormones begin the process of mobilizing energy, we expect them to spike up just like heart rate did. And you can see here that they do spike. This graph is of epinephrine, with the x-axis again showing you time in 10-minute intervals, and the y-axis showing you the amount of epinephrine in participants' blood. In this graph, you can see that there's a huge spike in epinephrine when the participants jumped out of the plane. And this graph is showing you norepinephrine, again with the same labeling of the x and y axes. The peak here is actually 10 minutes after the jump from the plane, so it's a bit of a delayed peak for this hormone. Notice that if you had only measured the hormone levels at the moment of the jump, you would have thought that the norepinephrine wasn't affected as strongly because you would have missed this peak. Now to look at the immune measures. They measured a variety of different immune measures. They couldn't measure these continuously, like the heart rate and hormones, but they do have these measures from 2 hours before, immediately after, and 1 hour after the jump. This slide shows two different kinds of natural killer cells. Natural killer cells are those soldiers that attack and kill cells that are infected with a virus. The left bar in each group of bars is baseline, 2 hours before the jump. The middle gray bar is immediately after the jump, and the right bar is an hour later. And what you can see here is that these cells show huge increases right after the jump, and then they go down to below baseline an hour later. So at the moment of utmost stress, your immune system is actually working better, not worse. But then, by an hour later, it's suppressed. From the skydiving study, it appears that after acute stress, natural killer cell activity increases. This aspect of your immune system is activated right along with the other parts of the sympathetic nervous system, and this makes a certain amount of sense. It would be adaptive to protect the person or animal from infection in this fast and easy way, if there were a sudden danger. But remember that this response decreases after about an hour. So for a short time it's increased, but then over time it's suppressed compared to baseline. On the other hand, after chronic stress, you see a decrease in this type of stress response. Natural killer cell activity is suppressed. That's what you see in studies of people under chronic long-term stress, like people who are caregivers for sick relatives or under significant ongoing job stress. Altogether, this makes sense. In the short term, your immune system is activated for a while, but then as stress continues, it becomes suppressed. So like the stress response and the rest of the systems of your body, in the short term, the response to stress is helpful and good, but in the long run, it can become dangerous to your body.